Welcome! In this session, we'll dive into solving LeetCode problem number 2053, kth distinct string in an array. This problem challenges us to identify the kth distinct string in an array, where a distinct string is one that appears exactly once. We'll explore the approaches to tackle this problem efficiently. Let's get started. In this problem, we are tasked with finding the kth distinct string in an array. A string is considered distinct if it appears exactly once in the array. To solve this, you are given two inputs, the array arr, which contains a list of strings, and the integer k, which specifies the position of the distinct string to return. If there are fewer than k distinct strings in the array, the output should be an empty string. The input array can have up to 1,000 strings, each consisting of lowercase English letters with a maximum length of 5. The value of k will also be between 1 and 1,000. The output is a single string that represents the kth distinct string, or an empty string if the conditions are not met. Let's look at an example to understand this better. Suppose the input array is arr equals a, b, c, b, d, and k equals 2. The output in this case would be c. Here's why: the distinct strings in the array are those that appear exactly once. In this array, the distinct strings are C and D. Since k is 2, we are looking for the second distinct string, which is C. This illustrates how the problem is solved by identifying distinct strings and selecting the one at the kth position. Now, consider another input with the same array, arr equals a, b, c, b, d, but this time k equals 4. The output here is an empty string. The reason is that there are only two distinct strings in the array, C and D, but k is 4, which exceeds the number of distinct strings available. Hence, the result is an empty string. In a third example, if the input is arr equals x, y, z, and k equals 1, the output is again an empty string. This is because there are no distinct strings in the array, all the strings appear more than once. Therefore, the result must be empty. The problem also includes several constraints and edge cases to consider. For instance, if there are no distinct strings in the array, the output will always be an empty string. Similarly, if k is greater than the number of distinct strings in the array, the result is also empty. On the other hand, if every string in the array is unique, then the kth distinct string is simply the kth string in the array, provided k is within the bounds of the array length. For an array with just one string, that string is automatically distinct, and duplicates at the beginning or end of the array must be handled correctly when determining distinct strings. These edge cases help clarify how the solution needs to be implemented to handle various scenarios. When tackling LeetCode problem number 2053, the goal is to identify the kth distinct string in an array, where a distinct string is one that appears exactly once. To approach this, we can consider a few strategies. The first is the brute force approach, where we count the occurrences of each string in the array. This is done using a dictionary or hash map to record frequencies. Once we have those frequencies, we traverse the array a second time to identify strings that appear exactly once, keeping track of how many distinct strings we've encountered. When we reach the kth distinct string, we return it. If there are fewer than k distinct strings, we return an empty string. This method is straightforward, with a time complexity of O(n) for counting frequencies plus O(n) for the second traversal, leading to an overall complexity of O(n). The space complexity is also O(n) due to the hash map used for counting. While the brute force approach is simple and easy to implement, it does require two passes through the array, which can be seen as a trade-off. To address this, we can consider an optimized approach that combines frequency counting and the extraction of distinct strings into a single pass. Here's how it works: as we traverse the array, we use a hash map to both count the frequencies and record the index of the first occurrence of each string. Once the array is fully processed, we can iterate through the hash map to extract distinct strings in the order of their first appearance. This reduces the need for a second pass through the original array. The time complexity remains O(n) for processing the array, as the iteration over the hash map depends on the number of distinct strings, which is generally much smaller than the total array length. However, the space complexity is still O(n) due to the hash map. While slightly more efficient in implementation, this approach introduces some overhead in managing both the count and the order. Another alternative approach involves using a custom data structure, such as an ordered dict. This structure inherently maintains the insertion order while counting the frequencies of strings. By leveraging this, we can streamline the process of keeping track of both the frequency and the order of appearance. In this method, we count frequencies using the ordered dict during a single traversal of the array. Once that's done, we iterate through the ordered dictionary to extract distinct strings in their original order. The kth distinct string can then be returned, or an empty string if there aren't enough distinct strings. The time complexity remains O(n), due to the traversal, and the space complexity is also O(n). However, this approach does come with additional memory overhead to explicitly maintain the insertion order, and the use of a less commonly used data structure might make the implementation slightly harder to follow. After evaluating these approaches, the brute force method emerges as the best choice for this problem. Its simplicity and clarity make it highly effective, especially given the problem constraints, which allow for efficient performance even with 2 passes through the array. While the optimized and alternative approaches offer minor implementation advantages, they do not significantly improve the overall time or space complexity. The key insight here is that the problem fundamentally revolves around 2 tasks: counting frequencies and maintaining the order of appearance. A hash map is perfectly suited for this, enabling us to count frequencies efficiently. By making a second pass through the array, we ensure that distinct strings are extracted in their original order. This simplicity, combined with its ability to handle the input size effectively, makes the brute force approach the most practical solution. When comparing the approaches, the brute force method strikes the ideal balance between simplicity, efficiency, and readability. The optimized approach, while slightly more compact, adds unnecessary complexity in managing both counts and order within the same pass. Similarly, the alternative approach using ordered dictionaries introduces extra memory overhead and might not be as intuitive for implementation. Ultimately, the brute force method is preferred because it leverages the problem's constraints effectively, ensuring correctness while maintaining optimal efficiency. By simply counting frequencies in one pass and iterating through the array in a second pass, we can solve the problem cleanly and correctly. This approach is particularly well suited for arrays of size up to 10 to the power of 4, making it the best solution overall. In this problem, we need to identify the kth distinct string in an array. A distinct string is defined as one that appears exactly once in the array. If there are fewer than k distinct strings, we simply return an empty string. To solve this, we'll break the problem into clear steps. First, we parse the input, which consists of an array of strings ARR and an integer k. Our task is to locate the kth distinct string while handling edge cases like an empty array or when k exceeds the total number of distinct strings. Next, we need to count the frequency of each string in the array. A dictionary, or hash map, is perfect for this because it allows us to efficiently count occurrences by storing strings as keys and their counts as values. This will help us quickly determine which strings are distinct. Let's take a closer look at the implementation details of these steps. To count string frequencies, we start by initializing an empty dictionary called frequency_map. We then loop through the array, and for each string, we update its count in the hash map. By the end of this iteration, the dictionary will contain each string as a key and its frequency as the associated value. Once we have the frequency data, we move on to identifying which strings are distinct. To do this, we traverse the array again, this time checking the frequency of each string in frequency_map. If a string has a count of exactly 1, it is considered distinct, and we append it to a separate list called distinct_strings. Maintaining the original order of the array during this step is crucial, as the problem specifically requires the kth distinct string in the original order. Finally, we determine whether the list of distinct strings has at least k elements. If it does, we return the k1th string, since indexing is 0-based. Otherwise, we return an empty string. The efficiency of this approach lies in our use of a hash map for counting string frequencies, which allows us to complete this step in O(n) time. Additionally, by traversing the array a second time, we ensure that the distinct strings are identified in the correct order, preserving the original sequence of the array. While building the distinct_strings list is simple, we can optimize further by stopping the traversal as soon as we encounter the kth distinct string. This saves memory, as we don't need to store all distinct strings unnecessarily. It's also important to account for edge cases, such as arrays with fewer distinct strings than k, very small arrays, or arrays with no distinct elements at all. To summarize, the algorithm relies on two key data structures, a hash map to store string frequencies and, optionally, a list to store distinct strings if we don't optimize for early termination. Let's analyze the time and space complexities of our solution. First, counting the frequencies of strings using the hash map takes n time, where n is the length of the array. Traversing the array again to identify distinct strings also takes n, resulting in a total time complexity of n. For space complexity, the hash map requires u space, where u is the number of unique strings in the array. If we use a distinct underscore strings list to store distinct strings, it adds d space, where d is the number of distinct strings. Therefore, the total space complexity is u plus d. This makes the algorithm highly efficient in both time and space, especially when compared to less optimal approaches that might involve sorting or additional data structures. Now, let's apply this algorithm to a concrete example to see how it works in practice. Consider the input array ARR equals A, B, A, C, B, D, and K equals 2. First, we count the frequencies of each string. The resulting hash map is frequency underscore map equals A2, B2, C1, D1. Next, we traverse the array to identify distinct strings. Only the strings with a frequency of 1 are considered distinct, so as we iterate, we find C and D in the original order. These are stored in the list distinct underscore strings equals C, D. Finally, we check if there are at least k distinct strings. Since k equals 2, we return the second distinct string, which is at index 1 in the list. Therefore, the output is D. This example demonstrates how the algorithm efficiently identifies and returns the kth distinct string while preserving the order of the input array. This Python implementation solves LeetCode problem number 2053, kth distinct string in an array. ### explanation of the code. Step 1 asterisk. We start by counting the frequency of each string in the input array ARR. This is done using a dictionary called frequency. We iterate through the array and update the count for each string. If a string already exists in the dictionary, we increment its count, otherwise, we add it with an initial count of 1. Step 2 asterisk. Next, we create a list of distinct strings from the array. According to the problem, a string is distinct if it appears exactly once in the array. We filter the original array and include only those strings whose frequency in the dictionary is 1. Step 3 asterisk. Finally, we determine whether the kth distinct string exists. Since k is a 1-based index, we subtract 1 to convert it to a 0-based index. If k is less than or equal to the number of distinct strings, we return the string at that index in the distinct underscore strings list. Otherwise, we return an empty string, as there aren't enough distinct strings to satisfy the request. ### efficiency. Time complexity asterisk. The solution involves iterating through the list twice, once to count frequencies, n, and once to filter distinct strings, n. Thus, the total time complexity is n. Space complexity asterisk. We use a dictionary to store the frequency counts and a list for distinct strings. In the worst case, the space complexity is n. This implementation is optimal for the given problem constraints and handles edge cases such as k being larger than the number of distinct strings, input arrays with no distinct strings, small or empty input arrays. The code is concise, clear, and adheres to best practices for readability and efficiency. This is the Java implementation of the LeetCode problem number 2053, kth distinct string in an array. The logic mirrors the provided Python solution, with key adaptations for Java. We use a hash map to count the frequency of strings and an array list to store distinct strings. The kth distinct string is retrieved using the 0-based indexing of Java lists. If k exceeds the number of distinct strings, an empty string is returned. This implementation leverages Java's type safety and collections framework. To solve this problem, we start by addressing example 1, where the input array is a, B, a, C, B, D, and K is 2. The first step is to count the frequency of each string in the array. We initialize an empty dictionary called frequency to keep track of how many times each string appears. As we iterate through the array, we update the dictionary. For instance, when we encounter a for the first time, we add it with a count of 1. Then b is added with a count of 1, and when we encounter it again, its count is increment to 2. Continuing this process for the entire array, we end up with the dictionary, a 2, b, 2, c, 1, d, 1, which shows us the frequency of each string. Next, we identify distinct strings, which are the ones that appear only once. To do this, we iterate through the array and check the frequency of each string. Here, C and D each have a frequency of 1, so we collect them into a list called distinct_strings, which becomes C, D. Now that we have the list of distinct strings, the final step is to retrieve the kth distinct string. Since k is 2, we use zero-based indexing to access the second distinct string, which is at index 1. In this case, the value is D. Therefore, the output for this example is D. Moving on to example 2, the input array is x, x, y, y, and k is 1. Once again, we begin by counting the frequency of each string. Starting with an empty dictionary, we add x with a count of 1, then increment its count to 2 when we encounter it again. Similarly, y is added with a count of 1 and increment to 2. By the end of this step, our frequency dictionary is x, 2, y, 2, indicating that neither string occurs only once. In the second step of example 2, we identify distinct strings by looking for strings with a frequency of 1. However, in this case, there are no such strings, so the distinct_strings list remains empty. For the final step, we need to retrieve the kth distinct string, but since k is 1 and the list of distinct strings is empty, there is no valid kth distinct string. As a result, the output for this example is an empty string, represented as. Now we proceed to example 3, where the input array is z, 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 y, and k is 1. In the first step of example 3, we count the frequency of each string. Starting with an empty dictionary, we add z with a count of 1, then increment its count to 2 and then to 3 as we encounter it multiple times. Afterward, we add y with a count of 1 since it appears only once. The final frequency dictionary becomes z, 3, y, 1. Next, we identify distinct strings by checking for strings with a frequency of 1. Here, y is the only string that meets this criterion, so the distinct_strings list becomes y. Finally, we retrieve the kth distinct string. Since k is 1, we select the first string from the distinct_strings list, which is y. Therefore, the output for this example is y. Here, we analyze the time complexity of the solution by breaking it into 3 main steps. First, we build the frequency dictionary by iterating through the input array. For each string, we perform a dictionary lookup and update, both of which are O(1) operations on average. Since we process every string in the array, this step as a whole takes O(n) time, where n is the length of the array. Next, we create the list of distinct strings using a list comprehension. This involves another iteration through the array, where we check the frequency of each string in the dictionary. Each lookup in the dictionary is O(1) on average, so this step also takes O(n) time. Finally, accessing the kth distinct string in the resulting list is a simple O(1) operation, as it involves a direct index access. By isolating these steps, we can clearly see how the time complexity is distributed across the algorithm. When we combine the time complexities of all 3 steps, we get O(n) for building the frequency dictionary, O(n) for creating the distinct strings list, and O(1) for accessing the kth distinct string. Adding these together, the overall time complexity of the solution is O(n). Now, turning to space complexity, we need to account for the memory used by the frequency dictionary and the distinct strings list. The frequency dictionary stores each unique string as a key and its frequency as the value. In the worst case, where all strings in the array are unique, the dictionary will store n key value pairs. This gives the dictionary a space complexity of OU, where U represents the number of unique strings. Since the number of unique strings cannot exceed the total number of strings in the array, U is bounded by n, making this part O(n) in space usage. Next, we consider the distinct strings list. This list contains all the strings from the array that have a frequency of 1. In the worst-case scenario, where all strings in the array are distinct, the list will contain n elements. This results in a space complexity of O(d), where d represents the number of distinct strings. Like the frequency dictionary, d is also bounded by n, so the space complexity for the list is O(n). Combining the space usage of the frequency dictionary and the distinct strings list, the total space complexity of the solution is O(u) plus O(d). Since both u and d are bounded by n, the overall space complexity is O(n). To put this into perspective, a naive approach using nested loops would result in a time complexity of O(n squared, as it would involve counting frequencies for each string individually. However, by leveraging a dictionary for efficient frequency counting and a single pass for filtering distinct strings, the optimized solution reduces the time complexity to O(n), while maintaining the same space complexity of O(n). Now, we assess the algorithm under different scenarios. In the best case, whether all strings are distinct or all are duplicates, the algorithm still performs 2 full passes over the array. This means the time complexity remains O(n), regardless of the input. In the worst case, the input size and structure do not change the number of operations, so the time complexity remains O(n). Similarly, the space complexity is O(n) in all cases, as the dictionary and list scale linearly with the input size. To mathematically verify this, the solution involves 2 linear passes over the array, one for frequency counting and another for filtering distinct strings. These linear operations dominate the time complexity, solidifying it as O(n). Additionally, both the dictionary and list grow in proportion to the number of unique and distinct strings, which is at most n, confirming that the space complexity is O(n). In conclusion, the algorithm is both time and space efficient, operating in O(n) for both metrics. When solving this problem, there are several common mistakes to watch out for. One frequent error is not handling duplicate strings correctly. For example, assuming a string is distinct without carefully counting how many times it appears can lead to incorrect results. It's essential to ensure that only strings appearing exactly once are considered distinct. Another pitfall is skipping edge cases, like when the array is empty, all strings are duplicates, or k is larger than the number of distinct strings. Your solution should be robust enough to gracefully handle these scenarios. Inefficient use of data structures is another issue to avoid. If you use a list for frequency counting, you'll end up with an O(n squared) complexity due to repeated searches. A better option is to use a dictionary or collections counter for efficient O(n) counting. Additionally, you need to validate k before proceeding. If k exceeds the number of distinct strings, your solution might return incorrect results or throw errors, so handling this gracefully is key. Finally, be mindful of iteration order. Since the kth distinct string is determined based on the original order of the input, losing track of that order can lead to wrong answers. Now, when tackling this problem in an interview, there are a few strategies that can help you stand out. First, always clarify edge cases with the interviewer. For instance, ask what to do if k is invalid or if there are no distinct strings at all. This shows that you're detail-oriented and thinking critically about the problem. Optimizing space and time usage is also important. A good approach is to use one pass to count frequencies and another to locate the kth distinct string, minimizing both time complexity and unnecessary space usage. Be prepared to explain trade-offs as well. For example, you can discuss the balance between using extra space, like a hash map, and achieving better time efficiency. This demonstrates a deeper understanding of the problem. Modularizing your solution is another key tip. Break your approach into clear steps, count frequencies, filter distinct strings, and finally locate the kth string. This not only makes your code easier to debug but also helps you communicate your thought process more effectively. Lastly, it can be helpful to connect this problem to related problems. For instance, LeetCode number 692 involves counting and ranking strings by frequency, while LeetCode number 387 focuses on finding the first unique character in a string, which is conceptually similar but simpler. Highlighting these connections can help you draw on prior knowledge and show the interviewer that you understand broader patterns. There are also alternative approaches to solving this problem, each with its own trade-offs. The two-pass approach is often the most optimal. In the first pass, you count frequencies using a hash map, and in the second pass, you iterate through the array to find the kth distinct string. This method is efficient, with a time complexity of O(n) and a space complexity of O(n), making it a well-balanced solution. A simpler but less efficient option is the brute force approach. Here, you iterate through the array for each unique string to count frequencies. While this method is straightforward, it has a time complexity of O(n squared, which makes it unsuitable for larger inputs. Another alternative is the sorting-based approach. After counting frequencies and extracting distinct strings, you sort them. While sorting simplifies the process of locating the kth string, the time complexity increases to O(n log n, making it less optimal than the two-pass method. For advanced users, there's the streamlined single-pass approach, which counts frequencies and tracks the kth distinct string in a single loop. While this method reduces the number of passes, it can make the code harder to read and debug. Choosing the right approach depends on the trade-offs you're willing to make between simplicity, efficiency, and maintainability. Great job! To summarize, we solved the problem by leveraging hash maps for efficient frequency tracking. Remember, edge cases are crucial to consider when implementing solutions. If you enjoyed this walkthrough, please like, share, and subscribe for more problem-solving insights. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!